Good morning, students. In today's lecture, we will discuss some important theorems related to noetherian modules. So in the first theorem, we will prove that every sum module and factor module of a noetherian module is noetherian. So let us take a noetherian R module M. We proved that every sum module of M is noetherian. Now we already discussed that an R module M is noetherian if and only if every sum module of it is finitely generated. Now, to prove every sum module of M is noetherian, let us take N is any sum module of M. And we have to prove that N is noetherian. Means every sum module of N is finitely generated. So let us take any sum module of N. Let this sum module is N1. Now, because N1 is a sum module of N and N is a sum module of M, therefore N1 is sum module of M. Now M is given to be noetherian, and by definition of noetherian, every sum module of M will be finitely generated, and N1 being the sum module of M, that will be finitely generated. So we have proved that every sum module of N is finitely generated. So this proves that N is noetherian. So we have proved every sum module of a noetherian module is noetherian. Now, in the second part, we will prove that every factor module of a noetherian module is noetherian. So let us take M is noetherian R module and M by N be a factor module of M. Now we have to prove that this factor module M by N is noetherian. It means we have to prove that every sum module of factor module M by N is finitely generated. So let us take A by N is any sum module of the factor module M by N. Now here this A is sum module of M containing N. Now M is given to be noetherian and therefore every sum module of M is finitely generated. Now here A is sum module of M and therefore A will be finitely generated. So by definition of finitely generated module, there will exist finite number of elements, say x1, x2, x3 and so on up to xn belonging to A, such that A is generated by these elements. So we have taken A is generated by the elements x1, x2, x3 and so on up to xn. So we can write A is equal to summation Rxi, where I varies from 1 to n. Now let us consider the elements x1 plus n, x2 plus n, x3 plus n and so on up to xn plus n. Now these elements are of the coset types. Here x1, x2, x3 up to xn, they belongs to A. So these cosets, they will belong to A by n. Now we prove that A by n is finitely generated. So let us take an arbitrary element x plus n belonging to A by n. Here x belongs to A. Now because A is generated by the elements x1, x2, x3 up to xn, so we can write x as a linear combination r1 into x1 plus r2 into x2 plus r3 into x3 and so on up to rn into xn. Here these r1, r2, r3 and so on up to rn, these are the coefficients from the ring R. Here this I varies from 1 to n. Now let us find x plus n. So x plus n will become r1 x1 plus r2 x2 plus r3 x3 and so on up to rn xn plus n. Now, by definition of addition in quotient modules, this addition can be written as R1 x1 plus n plus R2 x2 plus n plus R3 x3 plus n and so on Rn xn plus n. Now this element R1 x1 plus n, by definition of scalar multiplication in a quotient module, this element can be written as R1 into x1 plus n. In the same way, R2 x2 plus n, that can be written as R2 into x2 plus n. And Rn xn plus n can be written as Rn into xn plus n. So, we have written x plus n in the form R1 into x1 plus n plus R2 into x2 plus n plus R3 into x3 plus n and so on up to Rn into xn plus n. Thus, we have proved that A by n is generated by the elements x1 plus n, x2 plus n, x3 plus n and so on up to xn plus n. So this proves that A by n is finitely generated. Now, A by n is submodule of the factor module m by n. So we have proved every submodule of the factor module m by n is finitely generated. So by definition, this proves that the factor module m by n is noetherian R module. So this completes the proof of the theorem that every factor module of noetherian module is noetherian. Now, in the next theorem, we will prove the converse of this theorem. Means, if submodule and factor module are noetherian, then so is the module. So, the theorem is, let M be an R module, N be a submodule of M, such that N and M by N are noetherian. We are to prove that M is also noetherian R module. Now, to prove that M is noetherian, we prove that every submodule of M is finitely generated. So let us take an arbitrary submodule of M. So let A be any submodule of M. Now, N is also a submodule of M, and sum of submodules is again a submodule of M. So, A plus N is a submodule of M, and it also contains N. So, by definition, A plus N by N, that will be a submodule of the factor module M by N. Now, we are given that the factor module M by N is noetherian. So, every submodule of M by N will be finitely generated, and therefore, A plus N by N being the submodule of M by N, that will be finitely generated. Now, by isomorphism theorems of modules, A plus N by N, that is isomorphic to the factor module A by A intersection N. Now these two modules are isomorphic and this module is finitely generated, and therefore this factor module is also finitely generated. Now A intersection N, that is a submodule of M, and it is also contained in N, and therefore A intersection N is a submodule of N. Now N is given to be noetherian, and therefore every submodule of N will be finitely generated, and A intersection N is a submodule of N, so we can say that A intersection N is finitely generated. So let us take A intersection N is generated by the elements x1, x2, x3 and so on up to xm. These elements x1, x2, x3 up to xm, they belongs to A intersection N. Also, A by A intersection N, that is finitely generated. So let us take, this is generated by the elements y1 plus A intersection N, y2 plus A intersection N and so on, yn plus A intersection N. Here these y1, y2, y3 up to yn, they are the elements of A. Now we have to prove that A is finitely generated. So let us take an arbitrary element x belonging to A. So the coset x plus A intersection n, that will belong to the factor module A by A intersection n. Therefore, x plus A intersection n can be written in the form of a linear combination, because this factor module is generated by the elements y1 plus A intersection n, y2 plus A intersection n, and so on, yn plus A intersection n. So by definition of finitely generated module, this element x plus A intersection n can be written in the form of a linear combination. So by taking the coefficients rj from the ring R, here j varies from 1 to n. This element can be written as summation rj into the elements yj plus A intersection n. Here j varies from 1 to n. Now again, by using the definition of scalar multiplication in a factor module, this element can be written as rj yj plus A intersection n. So the element x plus A intersection n can be written as summation rj yj plus A intersection n. Here j varies from 1 to n. Now these two cosets are equal. So by definition, we can say that the element x minus summation rj yj, where j varies from 1 to n, this belongs to A intersection n. We have already taken that A intersection n is generated by the elements x1, x2, x3 and so on up to xm. It means A intersection n can be written as summation rxi. Here I varies from 1 to m. It means this element belongs to summation rxi. So by definition of this sum, this element x minus summation rj yj, where j varies from 1 to n, this can be written in the form of a finite sum by taking the coefficients from the ring R. So this can be written as summation si xi, where I varies from 1 to m. These si are the coefficients from the ring R. Here I varies from 1 to m. So from here we can find the value of x. So x can be written as summation rj yj, where j varies from 1 to n, plus summation si xi, where I varies from 1 to m. So we have shown that x can be written as a linear combination of the elements y1, y2, y3 up to yn and the elements x1, x2, x3 up to xm. X was an arbitrary element taken from A. So we can say that A is generated by the elements y1, y2, y3 up to yn and the elements x1, x2, x3 up to xm. So A is generated by finite number of elements. So we can say that A is finitely generated. So we have proved that every submodule of M is finitely generated. So by definition, we can say that M is noetherian modules. So this completes the proof of this theorem.